A warship, a colony vessel, an interstellar ark, all born in the void, never having known a planet's touch. What does it take to build entire fleets in space? Why build in orbit? For all of human history, ships have been built on land before they ever set sail. Even spacecraft so far have followed a similar pattern, constructed on Earth, carefully tested, and launched into orbit atop powerful rockets. But as we expand in the cosmos, a question inevitably arises. Why keep building ships on planets at all? If space is where they will live, why not build them there from the start? After all, you don't build a submarine on a mountaintop, so why build a spaceship at the bottom of a gravity well? The idea of orbital shipbuilding is not just a matter of convenience, it's a necessity for constructing the vast fleets that may one day populate the solar system and beyond. Launching a fully assembled spaceship from Earth is like trying to launch a fully built ocean liner from the bottom of an ocean. It's inefficient, expensive, and needlessly complicated. Just ask Emperor Palpatine, though admittedly that scene from Episode 9 did look cool. For the moment at least, all industry, workers, and manufacturing muscle remain on Earth. But to truly move beyond Earth's cradle, we must build our spaceships where they are needed, in space. The gravity well problem. One of the biggest reasons to shift shipbuilding into orbit is Earth's gravity well. Every kilogram of mass that leaves Earth must fight against its gravitational pull, requiring an enormous amount of energy. Right now, the cost to send material to orbit is measured in thousands of dollars per kilogram, making large-scale space manufacturing impractical. Even with the promise of cheaper launch systems like Starship, the fundamental problem remains. Launching from the ground means burning vast amounts of fuel to escape gravity's grip. You also have real constraints on how big a rocket can be, and thus how big any single component can be. By contrast, building ships in orbit eliminates the need for heavy booster rockets and payload fairings designed to survive the stresses of launch. It also removes all size limitations imposed by rockets, as well as gravity and wind. Many things can be built much more delicate and fragile in space, but not if they must be built down here and survive the brutal stresses of a launch. Instead of painstakingly assembling a spaceship on Earth and hoping it survives the trip to space, and having to engineer components to survive conditions it won't encounter in space, we could manufacture its components in microgravity and assemble them without the constraints of planetary launch systems. This becomes even more crucial when thinking about truly large spacecraft, ones measured in kilometers rather than meters, the kind we like to discuss for settling this galaxy and its trillion worlds, or the space habitats we want to build as alternatives to less habitable worlds. The sheer logistics of launching and assembling a colony ship, interstellar vessel, or an entire space fleet from a planet's surface would be daunting at best and impossible at worst. Orbital Shipyards solve this by starting in the environment where these ships are meant to operate. Material sourcing, the importance of ISRU. Of course, even if we build our ships in orbit, they still require raw materials, metals for hulls, silicon for electronics, and volatiles like hydrogen and oxygen for life support and fuel. Right now, every one of those resources has to be brought up from Earth, but that will not be a long-term solution for an expanding space industry. The key to making orbital shipbuilding practical is in-situ resource utilization, ISRU, harvesting materials from space itself. There are three primary near-term sources for these materials. 1. The Moon. Rich in aluminum, titanium, and silicon, the Moon is an excellent source of structural materials for shipbuilding, and we have devoted whole episodes to figure out how to harvest those. It also contains frozen water in its polar craters, which can be broken down into hydrogen and oxygen for fuel. The low gravity of the Moon, just 1/6 that of Earth, means that launching materials from its surface is far easier and cheaper than launching from Earth. 2. Asteroids. The asteroid belt, along with near-Earth asteroids, contains vast amounts of metal-rich bodies, many of which are composed of nickel, iron, and even platinum group metals. Some asteroids are mostly solid metal, providing a nearly unlimited supply of raw materials for the space industry. More importantly, asteroid mining eliminates the need to launch heavy metals for the planetary surface altogether, and we've also dedicated whole episodes to asteroid mining and settlement, though their low gravity might also make them good shipyards, not just mines. And, despite the episode name, we are not just contemplating shipyards orbiting Earth, or even other planets, but those orbiting the Sun too, like asteroids. 3. Gas giants and ice moons. Hydrogen and helium harvested from the atmospheres of Jupiter and Saturn could serve as valuable fuel sources in a fusion economy, while moons like Europa and Enceladus contain vast reserves of water ice, which can be used for life support, radiation shielding, and fuel, or propellant. By integrating ISRU into orbital shipbuilding, we can create a self-sustaining space industry, where materials are gathered, refined, and assembled into ships without ever touching Earth's surface. Early orbital shipyards, existing and near-future projects. Humanity is still in the early days of space manufacturing. Right now, every spacecraft is built on Earth and launched atop a rocket, a process that is both costly and restrictive. However, the shift toward orbital shipbuilding has already begun, with early prototypes and infrastructure paving the way for the first true space shipyards. Those first steps began even with the space shuttle era and continue to improve. In this section, we'll explore the first steps toward orbital spaceship construction, from existing space stations that have tested modular assembly techniques to upcoming projects that will shape the future of shipbuilding in space. We'll also revisit some of the concepts we explored in Spaceship Factories, including some fictional starship factories we outlined there, examining how they fit into this broader evolution into space-based manufacturing. Lessons from space stations and prototypes. One of the earliest demonstrations of orbital construction was the International Space Station, ISS, a structure assembled in orbit from multiple modules launched separately and docked together in space. While the ISS itself wasn't a shipyard, it proved that large-scale modular construction was possible outside Earth's atmosphere. The ISS also provided valuable insights into challenges of space construction, such as the need for robotic arms and EVA, extravehicular activity, to manually assemble structures, the difficulty of welding and attaching components in microgravity, and the long-term effects of space radiation and micrometeoroid impacts on construction materials. These lessons have informed more recent projects, such as NASA's Artemis program, which includes the Lunar Gateway, a planned space station in orbit around the Moon that would serve as a staging point for future missions. Though not a fully fledged shipyard, the Lunar Gateway would be one of the first facilities built and assembled entirely in space, setting an important precedent for more advanced orbital infrastructure. Private companies have also begun experimenting with orbital manufacturing, and to give credit where it is due, we have Axiom Space, which plans to build a commercial space station that will eventually replace the ISS with dedicated manufacturing modules. Sierra Space's Dream Chaser, a cargo vehicle aimed to provide logistics support for future orbital facilities. SpaceX's Starship, which could make launching heavy equipment for orbital shipyards far more economical. While none of these are shipyards yet, they represent the first steps toward a permanent industrial presence in space, and a place to test ideas and manufacturing principles for later expansion. Port George and Linus Scrapyard, revisiting fictional shipyards. In Spaceship Factories, we explore the idea of two orbital shipyards. Those were Port George, a government-funded, high-tech orbital facility that builds mid-sized spacecraft, and the Linus Scrapyard, a rugged, asteroid-based shipyard specializing in cheap, minimalist spacecraft. Both of these concepts illustrate different potential models for future orbital shipbuilding. Let's take a deeper look at how they fit into the larger framework of space infrastructure. Port George, a model for future orbital shipyards. Port George is a low-Earth orbit LEO shipyard designed to construct and maintain ships operating in cislunar space. As a high-tech facility, it prioritizes safety, automation, and efficiency, using telepresence labor, where workers on Earth remotely control robotic arms and drones to assemble ships in space. This approach reduces the cost of transporting people into orbit and maintaining the facilities needed to support them on and off duty, potentially including entire space-based communities. While such communities could serve as a catalyst for true space development, they require significant investment to establish. In the meantime, robots, both automated and remotely operated from Earth, provide a cost-effective solution. This is a unique advantage of orbital shipyards around Earth. They can draw on existing expertise in population centers, operating close enough for real-time construction and oversight without the need for permanent on-site workers. We also gave Port George the equivalent to a dry dock, a large thin-walled structure under partial pressure, though still in microgravity, which would make working on the ships there much easier. The thin membrane can even be penetrated by micrometeors and still give the workers plenty of time to evacuate before it depressurizes. This is not as resource-intensive as such a big structure might seem, as essentially an inflatable balloon, or perhaps two thin but rigid hemispheres, which you could simply pump the air out of and separate when the ship is done and ready to leave. Micrometeors or space debris hitting it would simply punch a small hole through in many cases, which would leak slowly, and also be easy to patch. Finally, Port George included ready access to the moon's materials, which reduces reliance on Earth-based supply chains. This model closely resembles what real-world shipyards in LEO might look like in the next few decades. A facility like Port George would likely be a government-backed or international project, similar to how the ISS was a collaboration between multiple space agencies, if built this century. But we could well imagine many such facilities, public and private, orbiting Earth in a century or two. Linus Scrapyard, the Wild West of space industry. By contrast, the fictional Linus Scrapyard we discussed in that episode is an asteroid-based shipyard located on Linus, the small moon of 22 Calliope, a large metallic asteroid in the belt. Unlike the high-tech, government-backed Port George, Linus Scrapyard is a rugged, independent facility specializing in low-cost, minimalist spacecraft built for asteroid miners, prospectors, and frontier operators, and maybe also pirates. Although it is technically an orbital shipyard itself, we really mean Earth orbital shipyards today, but I feel we need to think on asteroid-based ones as well to highlight the pros and cons of each. Labor at Linus Scrapyard is also very different from that at Port George. There are no telepresence workers here. Latency from Earth is too high for real-time remote control. Instead, the shipyard is staffed by a mix of automated systems and hands-on human workers, often asteroid miners who build or modify their own ships. Many of these vessels are no-frills, one or two-person craft, built for long hauls in deep space, but not necessarily high-acceleration trips, as they may not even have rockets, merely ion drives and compressed gas for those occasions they need a quick boost, making them much easier ships to build and requiring far less sophisticated manufacturing. The environment at Linus Scrapyard is also more extreme. There is no large dry dock or protective pressurized facility. Construction is done in open space, with workers operating in thin-walled, inflatable enclosures when necessary. The asteroid they are on has such low gravity that they could work right on the surface or even inside pressurized caves burrowed into the asteroid, or craters or mine shafts. These makeshift bubbles allow for low-cost, protected workspaces, but are far from the controlled environments of high-end shipyards. As the belt becomes more populated, similar facilities could become commonplace, forming the backbone of a decentralized, self-sufficient shipbuilding network in deep space. Infrastructure and logistics of orbital shipyards. Building ships in orbit is not just about assembling hulls and engines in zero gravity. It requires an entire industrial ecosystem capable of sourcing materials, manufacturing components, maintaining operations, and transporting finished vessels to their destinations. Unlike Earth-based shipyards, where supply chains are well established and logistics are straightforward, orbital shipyards face unique challenges in sourcing materials, energy, and labor while operating in the harsh vacuum of space. Unlike traditional shipyards, which are built along coastlines for easy access to waterways, orbital shipyards can theoretically be placed anywhere in space. However, some locations are far more practical than others. Low Earth orbit is the easiest location for early shipyards, benefiting from proximity to Earth-based expertise, resources, and supply chains. Early shipyards will likely source all but their simplest and bulkiest components from Earth too, relying on the moon for bulky but simple items like ship plating or actual fuel, water, and air. Shipyards in low orbit can take advantage of real-time communication with Earth, allowing teleoperated robotics to handle much of the assembly. But LEO has its downsides as well. The growing cloud of orbital debris poses an increasing risk, and atmospheric drag means that long-term facilities will require periodic station keeping to maintain their orbits. Moving beyond LEO, higher orbits reduce the risk of space debris and lower the fuel costs needed for ships departing Earth. The longer orbital periods could also help with shift coordination for workers, and a geostationary shipyard would allow for a single dedicated support facility on Earth with a constant direct line of sight to the shipyard. While this offers only minimal advantages, geostationary orbit might still be a popular location for shipyards if space elevators become viable. Such elevators would dramatically alter the economics of moving materials into space from existing industries on Earth, providing an alternative to in-situ resource utilization. We'll be exploring the economics of space elevators later this month. Yet, further out, the Earth-Moon Lagrange points provide more stable locations where shipyards could remain in position with minimal fuel expenditure. The L1 point, situated between Earth and the Moon, would allow for easy transit between the two bodies, making it ideal for servicing ships operating in cislunar space. L2, located beyond the Moon, offers a quieter, shielded location that could serve as a hub for long-term industrial projects. Both points offer easy access to the Moon's resources, which could significantly reduce reliance on materials launched from Earth. It is also vastly easier to build a space elevator off the Moon, whose low gravity allows existing materials like the aluminum abundant there to serve as space elevator tethers. A shipyard in lunar orbit or even on the Moon's surface could take advantage of local materials to construct spacecraft. The Moon is rich in aluminum, titanium, and silicon, making it an excellent source of structural materials. A surface-based shipyard could use the Moon's lower gravity to aid in certain manufacturing processes, while an orbital facility would allow for zero-gravity assembly without the dust contamination issues that come with lunar regolith. However, exposure to space radiation and the difficulty of transporting large amounts of material off the Moon remain challenges that would need to be addressed. For long-term deep space shipbuilding, the asteroid belt provides the best opportunity for self-sufficient industry. Metallic asteroids contain vast reserves of iron, nickel, and platinum group metals, making them natural locations for future shipyards. These facilities, like the Linus Scrapyard, would be rugged, independent operations, far removed from Earth's centralized infrastructure. The drawback to asteroid-based shipbuilding is that, at least in the early stages, the belt lacks the population and logistical support to sustain large-scale industry. Shipyards there would need to be heavily automated or require dedicated space habitats to house their workforce. Here we see why they will likely emerge, but long after the era of orbital shipyards, and indeed I could imagine some centuries down the road, the shipyards over Earth, once great titans of the space economy, being outcompeted in many sectors by local shipyards around other settlements in the solar system, with both supply of raw materials and demand for spaceships shifting to those locations. Transporting raw materials to shipyards is one of the biggest logistical hurdles in the space industry. Unlike on Earth, where cargo is moved by trucks, trains, and ships, space industry must rely on entirely different methods. One promising approach is the use of mass drivers or railguns, particularly for launching materials from the Moon's surface into orbit. Instead of relying on expensive rocket launches, a lunar mass driver could electromagnetically accelerate raw materials into space, where they could be intercepted by orbiting shipyards. Similar systems could be placed on asteroids, sending refined metals to shipyards across the solar system. These methods require significant upfront infrastructure, but offer long-term cost savings by eliminating the need for chemical rockets. Another option is the use of skyhooks, long tethers rotating through space that can catch incoming cargo and gently transfer it to orbital stations. A lunar skyhook, for instance, could capture materials launched from the Moon and lower them to a stable orbit with minimal energy expenditure. These systems would allow for far more efficient cargo transfer, reducing reliance on high-thrust propulsion systems. For moving materials over longer distances, orbital tugboats equipped with ion thrusters or solar sails could provide slow but efficient transport. These spacecraft, while not particularly fast, would be ideal for ferrying bulk materials like refined metals from asteroid mining sites to shipyards. Unlike chemical rockets, which burn through fuel quickly, ion propulsion allows for months or even years of steady acceleration, making it perfect for cargo that does not have a strict delivery timeline. Energy is another critical factor in shipyard operations. Unlike on Earth, where factories are connected to a power grid, orbital shipyards must generate all their energy on site. Solar power is the most practical solution for shipyards in the inner solar system, where sunlight is abundant. Large solar arrays could provide the energy needed for refining metals, operating robotic assembly lines, and maintaining life support systems for human workers. Some shipyards might even take advantage of space-based solar power systems, which could beam energy wirelessly across long distances to keep facilities operational. Shipyards in low Earth orbit also would have long night phases, as their orbital period of, say, 2 hours would have about an hour of that in shadow, necessitating power beaming to them or batteries. Those in higher orbits would have low percentages of shadow time, and for anything above medium orbit it is a minor concern, and the sun provides all the power they need, with minimal battery assistance and no concern of bad weather at any orbit, except solar flares of course. However, solar power becomes less viable as we move farther from the sun. Power and energy costs are vital to any manufacturing endeavor, so the more it costs or the less reliable it is, the less viable manufacturing becomes. For deep space shipyards, like asteroid-based ones, nuclear power may be the primary energy source. Fission reactors, particularly compact designs like molten salt reactors, could provide reliable energy for shipyards operating the asteroid belt or beyond. In the long term, nuclear fusion could revolutionize the space industry, offering abundant, high-output energy without the logistical challenges of fission fuel supply chains. Automation will play a major role in orbital shipbuilding, but human labor will still be essential in many aspects of the process. Robots will handle much of the heavy lifting, welding, and precision manufacturing, with AI systems monitoring production for errors. 3D printing technology will allow for components to be fabricated on-site directly from raw materials, reducing the need for pre-manufactured parts. However, humans will still be needed for quality control, repairs, and decision-making in situations where AI falls short. Orbital shipbuilding is far more than just assembling spacecraft. It requires a vast logistical network of resource extraction, transport, power generation, and labor coordination. The success of these shipyards will depend on how efficiently we move materials, generate energy, and integrate automation with human expertise. With the right infrastructure in place, orbital shipyards could evolve from isolated construction hubs into fully self-sustaining industrial ecosystems, capable of producing entire fleets without ever relying on Earth. Next, we'll explore what kind of ships and megastructures these orbital shipyards might produce, and how the process differs for everything from small spacecraft to kilometer-long colony ships. And if you enjoy thinking about the future of the space industry, there's even more waiting. In our latest exclusive episode, Fishbowl Starships, we explore how water might be the key to surviving deep space, not just a life source, but a shielding against radiation and kinetic threats. From icy tanks to aquatic habitats, it's a speculative dive into an idea that might help build the fleets we've been discussing today. We'll also examine all the other options for radiation shielding and ask how they stack up to plain old water. Nebula is a streaming platform built by creators for creators and audiences, and it's where you can watch every SFIA episode early and ad-free, including tons of exclusive episodes you won't find anywhere else, like our monthly Nebula exclusive episodes, and exclusive content from other great science shows like Real Engineering and Joe Scott. And with a Nebula annual subscription, you also get perks like guest passes to share with friends, or even lifetime memberships. You can get discounted lifetime memberships for $300 and unlock my entire archive of early, ad-free episodes, including dozens of SFIA exclusives and extended editions like Fishbowl Starships. Prefer something more flexible? You can also subscribe annually for just $36 a year. That's 40% off. Either way, head to go.nebula.tv/IsaacArthur and join us in gazing into our future. Constructing different types of ships. Building a spacecraft is far more than just assembling a hull and slapping on an engine. The types of ships constructed at orbital shipyards will vary greatly depending on their intended function, their level of available technology, and the scale of production. Some will be small, mass-produced vessels built in modular sections, while others will be immense megastructures assembled over decades. The process of constructing a personal space yacht is vastly different from that of a kilometer-long colony ship or a deep space warship. So let's step through the scales and types of ships that orbital shipyards might produce, from small shuttles to interstellar vessels, and the challenges involved in scaling up production from individual spacecraft to entire fleets. Small ships, shuttles, freighters, and tugboats. The first ships to be mass-produced in orbit will likely be small, functional spacecraft designed for near-Earth operations. These could include personnel shuttles, cargo freighters, and orbital tugboats, each serving a specific role in the growing space economy, most of which is in low orbit and thus where most of the demand for ships will be. Shuttles will serve as ferries between space stations, moving people and supplies between different orbital facilities. Unlike their modern counterparts, such as the SpaceX Dragon capsule, these next-generation shuttles won't need to survive high-speed atmospheric re-entry, allowing for simpler or more lightweight designs. Some may operate more like space taxis, carrying passengers between LEO stations and lunar outposts. Freighters will be responsible for transporting raw materials from mining operations on the Moon or asteroids to orbital shipyards. These vessels might rely on slow but fuel-efficient propulsion systems like ion thrusters, making long-haul cargo transport viable without the need for massive fuel supplies. Some freighters might be uncrewed, operating as fully autonomous drones that navigate predictable supply routes and aren't much more than a very large cargo pod. Of course, those shipping routes might eventually attract space pirates, which we've looked at in its own episode. Orbital tugboats will be small but powerful spacecraft designed to maneuver satellites, debris, and ship components within a shipyard. They will function much like modern tugboats in a harbor, using gentle but precise thrust to position large structures during construction. These vehicles may also be tasked with catching and redirecting cargo launched from mass drivers on the Moon or asteroids. Again, these small vessels will likely be the first to be mass-produced in orbit, as they require less infrastructure to build and will be in constant demand to support the growing space economy. Their modular designs will allow shipyards to manufacture them quickly, with interchangeable parts simplifying repairs and upgrades. Mid-sized ships, space habitats, transport vessels, and modular stations. Beyond shuttles and freighters, orbital shipyards will need to construct larger vessels capable of sustaining human crews for extended missions. These mid-sized ships could include long-haul transport vessels, smaller deep space habitats, and even modular space stations. Transport ships will be designed to carry people and cargo between Earth, the Moon, Mars, and beyond. Unlike chemical rockets, which are optimized for launching from planetary surfaces, these vessels will be designed for deep space travel, likely relying on nuclear or solar electric propulsion. Some might be designed as Aldrin cyclers, permanently cycling between Earth and Mars, reducing the need for continuous launches from planetary surfaces, or at least allowing lighter and less heavily shielded and outfitted spacecraft to launch, which can then dock inside the cycler for the trip. Space habitats will serve as long-term living environments for workers at shipyards, asteroid mining operations, and deep space research stations. These could range from simple pressurized modules to rotating structures that generate artificial gravity through centrifugal force, such as the Von Braun wheel or even the Kalpana 1 space settlement design. Some might even be equipped with bioregenerative life support systems, allowing them to sustain human populations indefinitely without resupply from Earth, or at least cutting down the resupply needs. Modular space stations, much like the International Space Station, will continue to evolve, serving as hubs for ship construction, refueling, and maintenance. Unlike traditional space stations, however, these stations will be built entirely in space, using resources sourced from the Moon and asteroids. They may also be fully expandable, allowing new modules to be added as demand grows, or even detaching and replacing existing modules as needed. These mid-sized ships and structures represent the transition from small, short-range vehicles to full-scale space habitats and interplanetary transport systems. Large ships, colony ships, warships, and megastructures. As shipbuilding technology advances, orbital shipyards will begin constructing truly massive vessels, ranging from interplanetary colony ships to heavily armed warships, and eventually megastructures designed for permanent habitation, which is also likely needed for interstellar colony ships due to trip duration being decades or centuries. Colony ships will be designed to carry thousands of people to new worlds, and they won't just carry settlers, they'll carry the future of civilization, whether that is to Mars, the moons of Jupiter, artificial habitats built in deep space, or off around new stars. Unlike current spacecraft, which are designed for relatively short missions, these ships will need to support human life for months or even years at a time, or even entire ecosystems. They may incorporate massive rotating habitats to provide artificial gravity, advanced closed-loop life support systems, and large cargo holds capable of carrying entire prefabricated settlements. Some designs may even resemble O'Neill cylinders, serving as self-contained ecosystems capable of sustaining a colony indefinitely. Warships, if humanity ever finds the need for them, which sadly we probably will pose unique engineering challenges. Unlike naval vessels on Earth, space warships won't need to worry about hydrodynamics or atmospheric drag, but they will need extensive radiation shielding, long-term power supplies, and highly efficient and powerful propulsion systems. They will also have to be built with redundancy and damage control in mind, as a single breach in the hull could prove catastrophic. Unlike planetary warships, which rely on fuel depots and supply chains, deep space warships will likely be partially self-sustaining, using onboard reactors for power and possibly even recycling damaged components into new armor or spare parts, or even including food, water, and air production and recycling, maybe even smaller mining shuttles so they can resupply fuel or other raw materials off asteroids or comets. The largest structures that might be built in orbit would be true megastructures, artificial worlds designed for permanent habitation. Bono spheres, Stanford tori, and O'Neill cylinders could eventually be constructed in orbit, providing homes for millions of people. Unlike traditional spacecraft, these structures wouldn't just transport humans across space, they would be humanity's first fully independent space settlements, capable of sustaining life indefinitely without reliance on Earth. While it might seem to make more sense to build a space habitat where it is needed, mass producing them in orbit and towing them to their destination, potentially after filling them with their initial population, might be more practical. They don't need to fit on a container ship, railroad, or highway. Size isn't a big deal in space. So too, the most popular spot for them is likely to be Earth orbital space anyway. These immense constructions would require entire fleets of automated drones, robotic fabricators, and self-replicating assembly units to be viable. They would also push the limits of material science and engineering, requiring advances in lightweight, high-strength materials and radiation shielding technology. However, once built, these megastructures could become the backbone of human civilizations beyond Earth, serving as the first true cities in space, and home to the work crews of these shipyards too. Challenges of large-scale shipbuilding. Scaling up from small freighters to kilometer-long colony ships will require significant advances in manufacturing techniques, automation, and logistics. While today's spacecraft are built in highly controlled environments with specialized teams, future ship construction will need to be far more streamlined. One challenge is standardization and modularity. Just as modern cargo ships use standardized shipping containers, future spacecraft must rely on universal docking ports, modular life support systems, and interchangeable propulsion units. This allows shipyards to mass-produce components that can be assembled in a variety of different spacecraft, reducing cost and improving efficiency. Another challenge is workforce availability. While automation will handle much of the heavy lifting, humans may still be required for oversight, maintenance, and design. This means that long-term space habitation will be essential for sustaining a skilled workforce in orbit. Early shipyards will rely on telepresence workers operating from Earth, but as shipbuilding scales up, permanent orbital and deep space settlements will become necessary. Finally, the sheer scale of resource extraction and transport required for building large ships will necessitate a fully developed space economy, where mining operations, refining facilities, and shipyards operate in a seamless supply chain. This will take time to develop, but once in place, it will allow humanity to construct not just individual ships, but entire armadas of exploration vessels, colony ships, and deep space habitats. The ships built in orbital shipyards will evolve over time, from small shuttles and freighters to massive interstellar colony ships and artificial space cities. The transition from individually manufactured spacecraft to mass-produced fleets will be a turning point in human expansion into space, making space travel routine and sustainable. But shipbuilding isn't just about producing vessels, it's about maintaining and upgrading them. In the next section, we'll explore the role of orbital shipyards in repairing, refitting, and sustaining entire fleets, ensuring that humanity's presence in space is not just possible, but permanent. Maintenance, repairs, and refits, sustaining a spacefaring fleet. Building ships in space is only the first step. Keeping them operational over years or even centuries is an entirely different challenge. Unlike terrestrial vessels, which can return to shipyards for repairs or upgrades, many spacecraft will operate far from any maintenance facility. Long-term sustainability will require a robust system of repair stations, refit docks, and mobile service platforms, ensuring vessels can remain functional no matter how far they travel. Space is an unforgiving environment. Even the best-built ships will suffer wear and tear. Micrometeoroid impacts, radiation exposure, and mechanical stress all take their toll. Without maintenance, even the most advanced vessel will eventually break down. Future orbital shipyards won't just build ships, they'll serve as repair depots, upgrading and sustaining entire fleets to keep spacefaring civilizations running. Routine maintenance in space. Even a well-maintained ship requires constant upkeep, and in space, small problems can quickly turn catastrophic. Unlike an aircraft carrier or cargo ship that can pull into a port for servicing, a deep space vessel may be years from a full repair facility. Hull integrity is a primary concern. Over time, spacecraft hulls accumulate microscopic damage from radiation and debris, gradually weakening their structure. While some materials might self-repair using nanotechnology or shape memory alloys, more extensive damage will require external repairs. Propulsion systems also demand frequent servicing. Ion drives, nuclear reactors, and fusion engines generate extreme heat and mechanical stress. Components wear down, fuel lines corrode, and reactor shielding degrades over time. Unlike chemical rockets, which burn out and are discarded, deep space propulsion systems must be designed for repair and refurbishment. Life support is another challenge. Air filters clog, water recyclers degrade, and radiation shielding weakens. On long-haul missions, especially aboard colony ships or generation vessels, these systems must be built for near-indefinite operation. Future shipyards will need to handle these refits, ensuring ships remain habitable for decades or even centuries. For most ships, returning to a full-scale orbital shipyard for major repairs will be necessary, but for those operating beyond the inner solar system, especially true deep space ships, like a Comet Minor, alternative solutions will be needed. Repair stations and mobile service platforms. Not every vessel can return to a shipyard. Deep space ships will require mobile repair stations, floating depots capable of servicing them en route. Some might be automated outposts stationed along key trade routes, maybe even Aldrin cyclers, offering refueling, minor repairs, and basic servicing much like gas stations on a highway. Other solutions will be entirely mobile. Ships equipped as roaming dry docks, essentially repair ships that are themselves shipyards, could travel alongside fleets, providing maintenance and upgrades without requiring vessels to return home. In the asteroid belt or at distant Lagrange points, these mobile shipyards could become critical infrastructure, roaming to smaller habitats and facilities on a cyclic or on-demand basis. Automated repair drones may also play a role. Instead of waiting for a ship to dock, these autonomous or teleoperated drones could be dispatched directly to vessels in need of servicing, conducting emergency repairs on the spot. For the most extreme cases, colony ships traveling between the stars, maintenance may become part of daily life. These massive vessels carrying thousands of people might resemble living ecosystems, with onboard repair crews constantly working to sustain the ship. Imagine a fleet of spacefaring leviathans, their repair drone flitting around them like schools of fish, fixing damage and keeping them running across the centuries. Refitting and upgrading older ships. Spacecraft are too valuable to discard when they become outdated. Instead, most ships will undergo periodic refits, upgrading key systems while keeping the core structure intact. New propulsion technologies like more efficient fusion drives or antimatter reactors could be installed to extend a ship's operational range. Life support systems might be swapped out for more advanced recycling methods, reducing reliance on supply missions. Even entire sections of a ship could be replaced, adding new habitat modules, expanding cargo holds, or upgrading radiation shielding. Some ships might be completely repurposed. A military vessel past its prime could be converted into a cargo hauler, research station, or mobile refinery. Likewise, an old freighter could be turned into a colony transport or emergency shelter. In times of war, civilian ships might even be rapidly modified into makeshift warships or Q-ships. Continuous upgrades will be essential for spacefaring civilizations. Unlike today's disposable satellite culture, future spacecraft will be built to last. evolving over time rather than being scrapped and replaced. Salvage and recycling, the ship-breaking yards of space. Even with constant maintenance, no ship lasts forever. Instead of letting derelicts drift as hazardous space debris, specialized salvage yards will be needed to break down old ships and recover valuable materials. Some facilities may orbit Earth or reside at stable Lagrange points, acting as dedicated recycling centers. Others might operate deep in the asteroid belt, repurposing old vessels into new spacecraft or habitats. Automated salvage drones could strip a decommissioned warship for useful components, while heavy industrial stations melt down hulls into raw materials. In some cases, retired ships won't be scrapped at all. A worn-out freighter might be towed to an asteroid mine and turned into a permanent outpost. A derelict station could be refurbished into a factory or a research base. When every kilogram of material in space is precious, the goal will be to reuse and repurpose as much as possible. A well-developed salvage and recycling industry will be critical to a sustainable space civilization, ensuring that every ship, no matter how old, serves a purpose until its very last bolt is melted down for something new. The future of orbital shipyards, expanding beyond Earth. The first orbital shipyards will be small, their ambitions tethered to Earth, but before long, they'll outgrow their cradle and start forging humanity's future among the stars. As humanity expands into the solar system, these shipyards will evolve from simple construction hubs into massive industrial centers, capable of sustaining entire space economies. The question is not just how we build ships in space, but what role shipyards will play in the greater tapestry of space civilization. Will they remain tightly controlled, government-backed projects, or will they become the beating heart of independent spacefaring nations, where fleets are born, maintained, and launched into the unknown? This wouldn't be SFIA if we didn't jump into the far future and ultra-big scale, so let's explore how orbital shipyards could evolve, from their early forms in Earth orbit to fully self-sustaining megastructures spread throughout the solar system and beyond. From assembly sites to fully integrated industrial hubs. Early orbital shipyards will focus on assembling ships from prefabricated components, much like how the International Space Station was built. These components will likely be manufactured on Earth, launched into space, and then put together by robotic arms or teleoperated systems. This approach will allow shipyards to begin operation before a fully developed space-based manufacturing infrastructure is available. Over time, however, shipyards will shift toward full in-situ manufacturing. As lunar mining and asteroid harvesting becomes routine, the need to launch materials from Earth will decrease, especially large bulk items like shielding as opposed to small microchips that cost little to bring up even from Earth relative to their cost and value, even at present. Future shipyards will include not just assembly facilities, but refineries, foundries, and automated factories, allowing for true industrial independence. Eventually, an advanced orbital shipyard might look more like a small city than a simple construction facility, or even a not-so-small city, as Kardashev-scale civilizations might require entire nations to build immense ships and structures. Workers will live on-site in space habitats, with entire economies built around shipbuilding, repair, and research. These shipyard hubs could become permanent population centers, supporting families, schools, and industries beyond just ship construction. The rise of megastructure shipyards. As technology advances, orbital shipyards will likely transition from relatively small construction facilities to massive space-based megastructures. Rather than floating stations assembling individual ships, entire moons or asteroids could be converted into fully operational shipyards, capable of producing entire fleets at once. One potential design for these megastructure shipyards is the Orbital Ring Shipyard, a structure that encircles an entire planet or moon, drawing materials from the surface and launching completed ships into space. Such a system would allow for near-continuous production and deployment of spacecraft, drastically reducing the cost and time needed to build new vessels. Another possibility is Lagrange point shipyards, positioned in stable gravitational pockets between planets and moons. These facilities would be safe from planetary debris and could act as supply depots, maintenance hubs, and launch points for deep space missions. Over time, Lagrange shipyards could grow into sprawling industrial complexes, with sections dedicated to manufacturing, ship assembly, and resource processing. As we discussed in our Lagrange point settlement episode, if you assume minimal station keeping, Those Lagrange points represent vast stable volumes of space in which many thousands of megastructures could be built like islands in a stable sea, unlike the more turbulent and changing map of orbital space. Privatization and the spacefaring economy. For much of human history, large-scale shipbuilding has been the domain of governments and powerful organizations. Today, the most advanced space missions are still conducted by national agencies like NASA, ESA, and a growing number of space agencies, but private companies are quickly catching up. The same shift will likely occur with orbital shipyards. Initially, space-based shipbuilding will be a mix of government and private industry, much like the International Space Station is today. Governments will invest in early infrastructure while private companies will refine the process and create more specialized facilities. Over time, private enterprises will establish their own independent shipyards, selling spacecraft and services to both governmental and corporate clients. In the long run, we might see entire economies built around shipyard hubs, where the construction and maintenance of space vessels become major industries in their own right. These could resemble modern-day free ports, where independent operators, corporations, and nation-states all compete to produce and maintain the best ships. However, this privatization also comes with risks. The possibility of corporate-controlled space infrastructure raises ethical and security concerns, as those who control shipyards will hold significant power over interplanetary trade, travel, and defense. As we like to say here, the sheer energy used to move spaceships around means there is no such thing as an unarmed spaceship. Nor can they afford to be unarmed, as they will likely need at least some point defense systems for dealing with micrometeors and debris. Regulations and treaties will be necessary to ensure that shipbuilding remains accessible and not monopolized by a few dominant players. Shipyards as strategic military and political assets. Shipbuilding has always been a strategic industry, and orbital shipyards will be no different. In any future where military forces operate in space, shipyards will be among the most valuable and vulnerable targets. A nation's ability to build and maintain fleets will determine its presence in space, just as control of shipyards and naval bases determine power on Earth's oceans. The militarization of space would likely lead to fortified shipyards, protected by defensive satellites, armed stations, and possibly even automated drone fleets. In a true interplanetary conflict, attacking or capturing enemy shipyards could determine the outcome of a war. Conversely, neutral or independent shipyards might become valuable diplomatic assets, serving as demilitarized zones where different factions can repair their ships and negotiate peace. We explored some of the options for that in our episode on orbital defense platforms. The political role of shipyards will extend beyond military concerns. Much like how coastal cities and port towns become major centers of culture, commerce, and power throughout history, shipyard hubs could evolve into the political capitals of spacefaring civilizations, hosting embassies, trade negotiations, and governing councils. If space colonization continues, we might even see the emergence of shipyard-based societies, where entire populations live and work in orbit, never setting foot on a planet's surface. These industrial space cities could develop unique cultures, economies, and governance structures distinct from planetary nations. And as mentioned, as we go to Kardashev scale or Dyson swarm numbers, the shipyards may even become nations themselves. The role of AI, automation, and post-human workforces. The workforce of future orbital shipyards may look very different from today's industries. While early shipyards will still require large numbers of human engineers, technicians, and laborers, advances in AI and robotics could significantly reduce the need for human workers. Indeed, we can't rule out that you might manufacture a spaceship in the future by shooting an asteroid with a pod of nanobots and waiting a few weeks for it to grow a ship. Though as we explored in our nanotechnology episode earlier this year, nanobots will be incredibly useful, but tend to get exaggerated in how fast they work and the assumption they do every job better than large-scale machines. And shipyards that build interstellar arc ships might have some very large-scale machines indeed. Automated assembly lines, self-replicating drones, and AI-managed logistics systems could make large-scale ship production possible with minimal human oversight. However, rather than eliminating jobs entirely, this shift might create a new class of highly skilled space workers, focused on overseeing, maintaining, and programming these automated systems. There is also the possibility that shipyard workers of the future may not be entirely human at all. If mind uploading, cybernetics, or AI consciousness becomes widespread, some shipyard facilities may be staffed entirely by digital minds, cybernetic, or robotic entities. These post-human workers could operate in hazardous environments without concerns for radiation, oxygen, or food supplies, allowing shipyards to be constructed in more extreme locations, such as high-radiation deep space zones or the atmospheres of gas giants. This raises philosophical and ethical questions. If AI construct all ships, who controls space travel? Could there be a future where AI-driven shipyards operate as independent entities, deciding which ships to build and who gets access to them? These are concerns that future spacefaring societies will need to address. For some fun reading, E&M Bank's cultural series examines the notion in detail and in an upbeat rather than depressing way. We often talk about new planets or asteroid mines as the driving force behind space settlement, but shipyards might have a better claim. Orbital shipyards will not just be factories, they will be the foundations of humanity's future in space. Starting as simple assembly facilities, they will grow into industrial megastructures, economic powerhouses, and even independent city-states. They will shape the expansion of human civilization, determining how we explore, settle, and defend the vast reaches of the cosmos. As the shipyards grow, so too will the fleets they produce, enabling humanity to push ever farther into the stars. From small orbital platforms to sprawling shipbuilding colonies, these facilities will become the beating heart of space industry, ensuring that our journey into space is not just a brief expedition, but a permanent expansion into the final frontier. To wrap up, orbital shipyards are more than just a means of assembling spacecraft. They are the turning point in human civilization. They mark the moment when we stop treating space as a destination and start treating it as home. From the first small factories in low orbit to vast shipbuilding complexes in deep space, these facilities will determine the speed and scale of our expansion into the cosmos. While early shipyards will remain closely tied to Earth, relying on terrestrial resources and expertise, the long-term trajectory is clear: self-sufficient industrial hubs capable of building entire fleets without ever needing a planetary supply chain. Over time, these shipyards will allow humanity to move beyond the limits of Earth's gravity well and fully embrace our future as a spacefaring species. The moment we stop treating space as a place we visit and start treating it as home is the moment we step beyond Earth for good. Orbital shipyards are not just about building ships, they are about building the future.